Good morning, West St. Paul. Mr. Pencharsky back today. Just going to be jumping into our second earthquake unit. So our first one, we just looked at earthquakes in general. We talked about fault lines, which are just cracks or boundaries between different tectonic plates. We looked at a machine called a seismograph, which measures earthquakes, and then we looked at what are called seismograms. These are just little printouts of what the earthquakes actually look like. We talked about how scientists who study earthquakes are called seismologists. We also examined the Richter scale and how different damage is caused by different magnitudes of earthquakes. And then you should have done the earthquake tracker assignment where you read about Dr. Holly Given and some information about her career, as well as what animals seem to have what organisms seem to have a little second sense, I guess, when it comes to detecting earthquakes. And finally, there was the earthquake plotting sheet where you plotted different earthquakes around the world. Now, today we're going to get into what are called seismic waves. Now, if you look at these photos here, we've talked about this one right here. This is the island of Santorini in Greece, and this is the island of Atlantis. And this volcano is a new volcano that's just forming here. We talked about seismograms, and this is a seismogram right here. This is just a printout from a seismograph of what the earthquake looked like or how it registered. And finally, this railroad track was built on a fault line. That's why it's that solid steel railway ties are bent right there. And finally, this is a shield volcano right here. This is in Hawaii. Now, we haven't talked about these last two yet, but we will coming up very soon. So let's jump into seismic waves. Now, there are three kinds of seismic waves produced by an earthquake. So when an earthquake happens, when these two large tectonic plates bump or slip or push into each other, they send out waves. And these waves are measured by seismographs and then sent by a seismogram to a seismologist who then determines the magnitude of the earthquake and can let people know that maybe there's more coming and can assess the damage. And also looks for patterns. So we have what are called P waves, which stand for primary waves, very, very small waves. They're fast. These are compact, but they're small. The S waves, which we call secondary waves, and of course the L waves are what we call long waves. So we're going to look at each one in a bit of detail. So starting with P waves, which are called primary waves. Now, these are the fastest waves. They are also known as compression waves because they're so tightly packed together. They're so fast that they can move through solids and liquids. They can travel through solids, liquids, and even gases. So if there was an earthquake right here in this little field here, the P waves would travel right through here, and if there was water, they'd even go through the water. They are the fastest and the smallest of waves. I'll go back if you missed anything there. Now, because these waves are so fast and they're so small, you often don't feel them. So if you were sitting on the surface of this field, you wouldn't even know if P waves were going through the earth. They don't cause the earth to actually shake. So these would be what would happen, for example, in a magnitude 1 earthquake. You wouldn't even notice it. Now, seismographs would pick them up, but that's the only way to know. Now, S waves, which are known as secondary waves, these ones come after the primary waves. They're much slower. And because they're slow, these waves can be felt on the surface, and they do cause damage. They're also known as side-to-side waves, and I'm going to show you what that means in a second. I'm going to do a little demonstration of how these waves would look. These waves only travel through solids. So for example, if the earthquake occurred right here on this fault line, the P waves would shoot off and keep going. The S waves would come a bit slower, but they'd go through as well. But if there was water here, The P waves would keep going, the S waves would stop. They do not go through liquids. They're too slow. When they hit the liquids, they dissipate. Now, lastly, we have what are known as L waves or long waves. They're also sometimes known as surface waves because you can actually see them on the surface. You can see the actual wave moving along the surface. These are the most dangerous of waves. They're the ones that will cause the most damage. They often aren't seen until you get into the magnitudes 7, 8, and 9. These are a double wave. So what that means is while they're traveling underneath the surface, there is another wave that's moving on top. They are the slowest waves, but they cause the most damage. So again, let's say this is our forest here. The P waves shoot right through. Don't even feel them. The S waves come next. They bounce around a bit. Their earth is shaking and moving all along. And if the L waves hit, if it's that much force, it is going to be on the surface. These trees are going to be toppled over. The whole up ground is going to be cracking and moving around. And again, this is what our seismogram printout. I believe this sheet asks you to draw one in. Now, I have a strange feeling that the sheet I uploaded may not have these next three things on them. And if they don't, please write them on the back side. But I think the one I upload will have it, though. Now, locating earthquakes. The time between the P wave and the S wave is used to calculate how far away the earthquake is. So there is a simple calculation that can be done to determine exactly where the earthquake started. Okay? And the scientists, the seismologists, will measure the time between the P wave and the S wave. And that will tell how far away the earthquake is. So they get the seismogram printout right here. Okay, here's your P waves, and now we have our S wave. So they measure the distance between these two, how long it took, and they could, generally speaking, pinpoint where the earthquake was going to be. But there is a problem with that, and let's take a look at this now. Let's just say that we have a seismograph right here, okay? And that seismograph detects an earthquake. Now, the scientists look at the P wave and the S wave, and they can figure out that it's about 200 kilometers away. Okay, but 200 kilometers in what direction? It could be in any direction. The station's here. All we know is it's 200 kilometers. So how do you think we would go about figuring out a more accurate idea of where it is? Now, if you said to yourself, well, maybe have another station, you're right. So this station over here reports that it's 75 kilometers away. So now we're getting closer. It's rather going to be here or here. So how do you think we can figure out which one it is? And if your guess was get a third station, you're right. So here's our third station. It's a big one. It says it's 1,000 kilometers away, but look here. It intersects right here. So the answer is you need 3 stations, 3 seismographs to accurately pinpoint where an earthquake starts. And that's why on these fault lines, there are tons of seismographs in the Earth's crust so that scientists can accurately track where they are. So 3 is needed. 3 seismographs are needed to pinpoint the source of an earthquake. So here's another rough example. We have a station here in England that picks up an earthquake 4,800 kilometers away. Another one here in Brazil picks it up as 3,400 kilometers, and one here in New York picks it up as 2,800. So they all converge right here in the middle of the Atlantic Ocean. And there is a fault line right there. Now, we're going to look at 3 final terms today, and the first one is called the focus. Now, the focus is the place deep in the Earth's crust where the earthquake begins. So if we look over here at this diagram, right here in the Earth, this is where those plates touched. This is where they pushed against each other, and that is called the focus. It's the place deep in the Earth where the earthquake begins. It's where these waves start from. It's where the contact was first made. Now, the epicenter is the place on the surface directly above the focus where we feel the damage. So for example, here's where the earthquake begins, but this is where we actually see the results of that earthquake. And we call that the epicenter. You would have seen this term on the Mercalli scale worksheet. So for example, here was an earthquake that happened in India, just on the Pakistan border. This is the epicenter, but those waves radiated out very, very far from that epicenter. It's the place on the surface, right above the focus, where the earthquake is first felt. Lastly, there's a term that you also would have seen in your Japanese megaquake video called a tsunami. And a lot of you are familiar with this term. This is a tidal wave caused by an underwater earthquake. Many of the fault lines on our planet are underneath oceans. And when those plates collide, they send out usually tsunamis, not always, depending on the magnitude of the contact. And these tsunamis can be absolutely devastating. We've seen them in countries from India, Indonesia, Sri Lanka. We've seen massive damage. And we're going to look at some right now, if I can get there today. Here we go. So here are some GPS satellite images of various locations before and after tsunami. So here's the first one. It's a little oceanside community, some houses, some businesses, some trees, some parks. Looks quite nice. Look what happens after the tsunami hits. So the houses are gone, the businesses are gone, the trees are generally gone, except for some probably very strong ones here. A lot of the land is just completely gone, like it's washed out. The flooding was so great that the land simply just vanished underwater. Bridges are knocked out. It's complete devastation. Here's another one. This is more rural. So this is an open field, a lot of farms, a lot of trees, a lot of maybe some farmhouses, some small communities here. And of course, right by the ocean as well. We got a beach over here, a really nice beach, big soil deposit. Let's take a look. So as you can see, the farms are all gone. The houses are completely washed away. The grasses and fields are dried out now and gone. They will grow back because, of course, one thing the tsunami does is bring nutrients with it. So the things will grow back. It's just going to take a lot of time. Some of these larger trees did survive the wave, but a lot of area here is washed out. Okay, so here's another little rural community. Some of these are very close to each other, by the way. So we have, again, some houses, some small things. These are all satellite images, by the way. And there you go. I like this one. So this is a cape, okay, which is a point of land that juts out into the water. You might have remembered that from our very first unit, sometimes known as a peninsula. And here we have a large urban development. So lots of houses close together, big streets, nice long beach right here. Probably some businesses, some forested area here. And there you go. So most of those businesses have been washed out. Most of those houses are gone. Some buildings still standing, but not many. As you get farther inland, you'll see less damage, but still damage. The beach is all washed up. Again, if you were living here, you're going to have to rebuild. This is completely destroyed. And unfortunately, most of the people in the world tend to live near water, near oceans. Some of the world's biggest cities, whether it's Tokyo, Japan, Beijing, China, New York City, Los Angeles, these are all cities that are right on the oceans. This is a further up shot. So this is the same one as before, but just further up. You can see kind of washed out. Closer up shot. Same area, but just closer up. You can see some houses did survive, but a lot of them didn't. And even if they did survive, they're probably so heavily damaged, you're just going to need to rip them down. Here's a close-up shot of that cape. So you can see the warehouse here was probably really well built. It stood through it, but everything else was washed out completely. And again, we're going to end off there. You guys would have seen some of that. If you want to see more about tsunamis, go back to that megaquake video if you didn't watch the whole thing, because you'll see some really cool some shots there of that. Guys, we're done now with seismic waves. I'm going to be doing a demonstration for you to attach to this video, simulating what seismic waves look like using a slinky. So check out that other video if you can. And finally, in addition to that, we're going to be looking at the layers of the Earth next. And then we're moving on from earthquakes to our final science lesson in this unit, which is called continental drift. So we're going to look at how the world was formed and why these fault lines exist today. Nice talking to you guys. See you soon. Bye now.